Konnichiwa. Thank you so much for having us here today. My name is Rohil Bhatnagar. I am in 12th grade in the Academy for the Advancement of Science and Technology.
Hi, my name is Rachel Yang. I'm in the 11th grade and I'm in the Academy for Engineering Design Technology.
We are representing the Bergen County Academies. Before we begin to explain the details of our project, we would first like to give a brief description of our school. So, the Bergen County Academies is a regional public magnet high school. It is located in Hackensack, New Jersey, in the United States, and is composed of 7 academies, including science, engineering, and business, which are all represented here today. We are also recognized by the U.S. News and World Report as one of the top high schools in the United States. Now for our project, High Altitude Balloon Experiment. A brief overview of what we did. We built a system using an SD, or Secure Digital Logging Shield, attached to an Arduino Duino microcontroller board to obtain data on temperature, pressure, and radiation levels. During the course of our experimentation, we had several modifications to our design. This is a schematic or drawing of our first design. You can see the central piece is the Arduino Duino microcontroller board. This is sort of like the brains of the whole experiment. What that means is that this was used to obtain the data on temperature and pressure. Attached to the Arduino, we have a power source, real-time clock, pressure sensors, and a thermistor, which was used to measure temperature. The data obtained by the Arduino was then written onto the SD logging shield, so that we could then read the data on our computers. Our first launch was a tethered launch. This happened in May of 2012 from our high school, the Bergen County Academies. Our system was attached to a weather balloon, which reached an altitude of approximately 100 meters. From this launch, we obtained data on temperature and pressure, which Rachel will now explain.
Alright, so for this graph, for this graph, this is temperature in Celsius versus time. This is the data taken from the thermistor. This first part was when we assembled the equipment indoors. And this part over here is when we brought the equipment outdoors during the tethered launch. So the consistency in the data in this section at about 27 degrees Celsius showed that our thermistor was working. Afterwards, this section over here is just when we brought the equipment back indoors, which explains the spike in temperature. So to improve upon our first design, in our second design, we added in another sensor, specifically a Geiger counter. And the purpose of the Geiger counter was to measure the radiation levels in the atmosphere. So as you can see here, this is the Geiger counter. This is the tube that's used to measure the radiation levels. We also added in 2 temperature sensors in addition to our thermistor. And over here, this is just the Arduino board, and this is the power supply. So when you put these 2 components together, you essentially get our entire data collection system. So this schematic summarizes all the changes that we made to our first design. As you know, we added in another sensor, the Geiger counter. And we also added in 2 temperature sensors in addition to the thermistor. To test our equipment, we ran 3 trials indoors at our school, BCA. Each trial was 4 hours long, and the consistency in our data between each trial showed that our equipment was working. So this is an example of one of our runs. Over here, this is temperature in Celsius versus time. And this was data taken from the thermistor. The consistency in data over here at about 33 degrees Celsius proved that our thermistor was working. In our second graph, this is radiation in counts per minute per time. And the general trend at about 25 counts per minute proved that our Geiger counter was working. Finally, in this graph, pressure in pounds per square inch versus time, and the data was consistent at 14 pounds per square inch, and this showed that our pressure sensor was working.
We also had one untethered launch. This launch happened on Saturday, October 13th, and we launched the system attached to a weather balloon, as you can see here, from Pennsylvania, so that the jet stream, or the wind, would not blow the system over the Atlantic Ocean. The launch itself was successful. However, we lost the equipment. We know that we lost the equipment because the GPS signals got interrupted, and we believe that they may have gotten interrupted by the noise or the pulses generated by the Geiger counter when it was measuring radiation levels. Here are some more pictures of our launch. You can see us filling up the weather balloon in this picture. Here is a picture of the payload, which contained our system attached to the weather balloon. And here is a picture of our system itself. You can see the Geiger counter right there. And the central piece, again, is the Arduino Duminolov microcontroller board. This is our system attached to the weather balloon in flight, and it reached an altitude of approximately 30 kilometers.
So in the future, we plan to run further testing to confirm that the Geiger counter was the cause of the interference of the GPS signals. We also would like to condense our apparatus to make it more compact. And in order to do so, we are currently designing an Arduino shield for the Geiger counter to eliminate any unnecessary components. Our long-term goal is to create a menu of sensors from which the user can choose which sensors to use to measure different parameters in the atmosphere. In May, we plan on having a joint launch with Kokutaiji High School at BCA, and we will be combining both projects together. We will launch our data collection system and use Kokutaiji High School's parachutes. So to conclude, we would like to thank Kokutaiji High School for inviting us to Japan and welcoming us here. We would also like to thank Dr. Kamara for his help and guidance, as well as our school, BCA, specifically Mr. Leva, Mr. Davis, Mr. Tarnike, and Mr. Paul. Thank you.
Now, I would like to introduce my fellow students, Matthew Lemash and Bejamin Judd, who will be presenting their work on Mission to Mars.
Good afternoon, ladies and gentlemen. My name is Matthew Lemash, and this is my partner, Ben Judd. Today, we will be introducing a new class at BCA inspired by Dr. Kumarda, Mission to Mars. The purpose of this class is to develop new methods of not only getting to Mars quickly and safely, but also in creating a sustainable habitat for the astronauts. These are problems that have been part of space travel since its beginning, so it's the responsibility of the students to develop new and innovative solutions for these issues. The class is 2 hours long and begins with a short lecture introducing the day's topic. The students then break up into small groups and work on creating solutions for these issues. Each week, the students present their ideas to the class, which allows for peer review and only the best 2 or 3 solutions to be chosen.
Students in this class hope to find solutions to problems associated with getting to and staying on Mars. These problems include shielding and protection from galactic cosmic rays and solar particle events, finding a good method of propulsion that will get us quickly to and from Mars, as well as finding a power source that will last the entire journey. On Mars, astronauts will need a good location that will protect them both from the elements and from galactic cosmic rays. Additionally, we would hope to build life cycles on Mars similar to those of Earth's. Solutions generated by students to these problems include using microalgae as a source of oxygen and food, as well as using the water surrounding the algae as protection from galactic cosmic rays. Another idea is to create a magnetic field aboard the spacecraft that will function similarly to that of Earth's. A third idea is to use hydrogen-rich materials, which will prevent the spallation of GCRs, thus protecting the astronauts. Here, students have analyzed the good and bad points of different methods of protection.
This image, while not exact, demonstrates the critical and creative thinking done by the students as they work to tackle the many challenges of space travel and exploration. Thank you.